So today we're going to be listening to Topic 3, Lesson 1, which is about the history of the atom. So a lot of times I get questions from students about how can I say this is what an atom is made of, or this is what an atom looks like, or this is what an atom does, because we can't even see them. So if we cannot see an atom, then how do we know that they even exist? Well, luckily, in the school that I'm teaching now, I can explain that a little bit easier because there are many things in life that we know of and believe in that we cannot see. And how come we know that they exist? Well, we have lots of pieces of evidence that would substantiate that what we are believing is true. So how can we know that an atom exists if we can't see it? Well, we have multiple pieces of evidence that creates the picture for us, just as we do for our faith. The first person who helped to create this picture was Dalton, and so I'm going to talk about Dalton's part in the atomic theory. Around 1803 or 1805, Dalton did many experiments in which he came up with the idea that elements are the tiniest particles and that they are indivisible. They're basically all of matter is made up of these little tiny marbles, I guess you would say. They are indivisible and they're the tiniest particles possible. We actually know now that that is incorrect, that they are tiny particles and we do still call them elements, but these tiny particles are not the tiniest of particles. We have things called subatomic particles. He also said that all elements of the same atom are the same. And we also know at this time that that was incorrect as well. There are multiple types of carbon atoms. There's multiple types of nitrogen atoms. All of our elements have different types of atoms of them. And some parts of them, like their proton number, is always the same. Carbon always will have 6 protons no matter what kind of carbon you are. But there are other parts of the carbon atoms that are different. So not all elements of the same atom are the same. There's different types of them. And again, those are other things that we'll be getting into later. He also stated that atoms of each element are different from each other, and that he is correct on. So a nitrogen is different than carbon, is different than potassium, is different than polonium. All atoms of each element are different from other elements. And lastly, he said that compounds consist of different elements chemically combined together, and we did learn that in the first unit, that if in order for it to be called a compound, they have to be different elements chemically combined. And Dalton recognized that as well. He got us on the path to exploring these things called atoms or elements. Now, how many atoms make up an orange? It's important for you to understand how small these things are, which is why we cannot see them. And it was hard for us to discover them and discover different aspects about them. So let's put in perspective how small an atom actually is. So if you took an atom and you wanted to figure out how many atoms you'd have to put in this funnel to fill this orange up, I'm going to do an analogy to help you to realize that. It's many, 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 many. So let's just say we take this orange and we blow it up to the size of the Earth. Because that's what I'd have to do for you to understand and pick an object that would be representative of the atom to the object it's filling. So let's take this orange and blow it up to the size of the Earth. And I'm going to put a funnel into the Earth and I'm going to fill this Earth with an object. And that object is going to represent an atom, or how many atoms it would take to fill up the orange is the same as the amount of cherries that it would take to fill up the Earth. So if you think about how small a cherry is and the massive number that that would be and need to be to fill the Earth, not to cover the Earth, to fill the Earth, you can understand that massive number in terms of atoms, how many atoms it would take to fill up an orange. So a ginormous number. Its atoms are extremely, extremely small, and we'll be doing, again, an application of that in class. So the next person after Dalton was J.J. Thomson and his atomic theory, what he had to add to the atomic theory. And this was about almost 100 years after Dalton. So this is around 1897, not really too long ago, and if you're thinking about in terms of time of history, just a little over 100 years ago. And what J.J. Thomson discovered was that electrons, he discovered electrons, and that they're negatively charged particles inside of the atom. So where Dalton said that the tiniest particle was an atom, Thomson's saying, there's some stuff inside of an atom, and one of those things is an electron, and I know that these things called electrons, that I'm calling electrons, are negatively charged. And he did that with an experiment, which I will be showing you in a video. He also said that the atom is a positive area wherein the electrons are all over it and inside of it. And so sometimes they used to call this the plum pudding model, but since we really don't eat plum pudding much anymore, I like to call it the cookie dough model, whereas the dough itself would be the positive area, and then the chocolate chips would be the electrons that are actually just scattered without that entire dough. He found this out and did discoveries with this thing called the cathode ray tube experiment. So at this time, I'm going to have you watch a video on the cathode ray tube experiment. Please make sure, again, that you are taking notes, pausing when you need to throughout the podcast, and then also writing down any questions that you would like me to explain further in class.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
So after your video, we're now going to be talking about the next scientist who added to our atomic theory, which is Ernest Rutherford. And this was in 1899, so this was not very far after the cathode ray tube experiment and Thomson's cathode ray tube experiment. Now remember that Thomson said that it was a positive sphere and that there were electrons that were embedded in this positive sphere, and he knew that because of the bending of the light during the cathode ray tube experiment. Well, Ernest Rutherford just wanted to make sure that this was true. And so he conducted what we call the gold foil experiment, which I will also show you a video on that at the end here. But what he discovered with this gold foil experiment was that most of an atom is actually empty space. And now Thomson thought that as well, but Rutherford was able to prove it with his gold foil experiment. So most of an atom is empty space. And then he also was able to prove that there is an extremely dense center called the nucleus. He said it was so dense that what it was like is if you had a paper towel and you shot a cannon at that paper towel, we would think, because an atom is mostly empty space, you would think that that ball would go straight through that paper towel. And that's what Thomson thought, and that's actually what Rutherford thought too, until he did this experiment. And when he did this experiment, what he found out was that some of the cannonballs got bounced back, like a cannonball got bounced back off of a paper towel, something extremely thin like that. So in order for something to be bounced, a cannonball back, it had to be extremely dense. And the nucleus is so extreme in terms of its density, we can't even really fathom it. If we tried to put an atom in our hand, the density of that nucleus would tear our arm right off. That's how dense that is. It would bounce a cannonball off of a paper towel. So he mathematically, with the Scofield experiment, was able to prove that the nucleus, that there is a nucleus first of all, and that it's a dense center. He also proved that that nucleus was positive, because what he did was he shot positives at this gold foil, which you will see, and because it bounced back sometimes, the opposites attract, but like repel. So because it actually bounced back, whatever it hit had to be positive as well. So he knew not only was it dense, but it was actually positive. And so he called those protons. This is a picture of the cathode ray, of the gold foil experiment. And this is that gold foil, or that, what we want to equate to a paper towel. That's how thin it was. And again, because empty space, an empty atom is empty space, it all went through. And he thought all of it would go through based on what Thomson said. But then he saw that some of it bounced back. And so he's like, what it hit, because I'm shooting positives at it, what it hit must have been positive. And since only a very few bounced back compared to all the others that went through, it must have only hit a few times, and therefore it must be extremely small. Dense, small, positive. Very important. Rutherford's gold foil experiment is one of those experiments which you definitely need to know. So now what I'm going to do is I'm going to show you a video of Rutherford's gold foil experiment, as well as a second video on just how small the nucleus actually is.
Ernest Rutherford with Hans Geiger and Ernest Mars covered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
So we've already talked about how big, or really how small the atoms are. Atoms, of course, are really small. It's the number of atoms in the orange is equal to the number of cherries in the earth. But now we want to look at the cherries. So I don't have any cherries, but I have a ping pong ball. So let's say the ping pong ball, it's a little bigger than a cherry, but pretend this is now, how big is the nucleus inside of the atom? And of course the nucleus would be like the core, the center. It would be the pit of a cherry, right? But how big is that pit? That's what we want to look at. And so to illustrate that, we're here at the Woodland Park football stadium. And so what we really want to do is to say, how big is that? Okay. Now I've also brought with me one other thing. It's a tiny little bean. Okay. So this would be like the size of the pit that you would put inside of the cherry. Is this the right size? So would this be appropriately sized for the nucleus? Well, the answer is no. We're going to actually have to blow the nucleus up, or probably the atom up, to the size of the football stadium. if you blow up the ball to the size of the football stadium, it's unbelievable.
So Mr. Bergman is down there on the 50-yard line. He's got his little bean, and that bean is the nucleus of the atom. And the whole radius of the atom is about the size of this football stadium. That's huge, and the nucleus is really, really tiny. The crazy thing is almost all of the mass of the atom is in that nucleus, is in that bean. So think about the most dense bean in the world you could possibly imagine. We're talking like tear your arm off dense. It's so heavy for such a small size.
So now we're getting to 1913, so about 15 years later. So now we're discovering things pretty quickly now. And we come up with Bohr's atomic theory, which is what you probably are used to at this point and have learned in the past. And this is about as far as you've gone. That's that theory where you take and you put how many protons and neutrons in the center, and then you put your electrons and these energy levels on the outside, because that's what Bohr did. Bohr studied light. He studied quantum physics, and we're going to talk about quanta again in a lab that we'll be doing. And when he was studying quantum physics, he was able to determine that electrons actually have specific amounts of energy. And so based on the energy that they have, they actually are orbiting, as you can see here. They actually stay in a shell and they orbit. And depending upon how much energy that electron has, depends upon what orbit it's in. Well, he was right that the electrons have different energy, but he was wrong with the orbit aspect. So again, he did say each energy level has its own energy amount associated with it, and that is correct. But what he's incorrect about is that the electrons actually orbit. There were multiple scientists who helped to add to Bohr's atomic theory and disprove the whole orbiting thing. But the whole energy and electrons having energy, and depending upon where they're located in relationship to the nucleus and what energy level they are, how much energy they have, leads us to our application of fireworks. And we're going to basically, again in lab, going to be showing you how different elements will give off different colors of light based on their energy levels and where their electrons are located in their energy levels. So we'll be going into that a little bit more later as well. And lastly, our modern theory is the wave mechanical model, and there's multiple scientists and still scientists who are adding to this model. So there's not a particular scientist that we are going to attribute this to, but you can see the wave mechanical model. Two pictures here. This one shows a little bit more what we're going to call orbitals, some s orbitals and p orbitals and whatnot. And this one just shows that it's pretty much a cloud. So sometimes it's called the electron cloud model. So make sure you understand that. Sometimes it's called the electron cloud model. What the wave mechanical model or electron cloud model states is that electrons do not orbit, but instead they're constantly moving in a given area. They're kind of like, gosh, I should bring a picture of this up. It's kind of like when you watch Charlie Brown, I think of the Pigpen and the dust particles that are always around Pigpen. They're not like orbiting around Pigpen. They're just kind of like in an area around Pigpen. And that's kind of what electrons do. They are within a given area density around the nucleus, and depend upon how much energy they have will depend upon how far from the nucleus they're going to be. But they're within a given area. That given area is called an orbital. So an area in which electrons are most likely to be found is called an orbital, and that is a vocabulary word that you'll need to know. So that is basic history of the atom. You will need to know in order how we got to the modern model, or the wave mechanical model, or electron cloud model of the atom, and also those two experiments, the cathode ray tube experiment by Thomson and the gold foil experiment by Rutherford, who's responsible for which experiment, as well as what those experiments contributed to our theory in terms of atoms.